Welcome geologists and guests to a video short especially prepared for the 2023 Ohio University Geologic Sciences Alumni Symposium. I'm Gregory Charles Herman, and it brings me great pleasure to present a synthesis of my new book titled Punctuated Tectonic Equilibrium that accounts for the periodic and catastrophic geological disruptions that Earth and Mars are subject to, and that are characterized here using geophysics and geographic information systems. So please sit back for the next half hour and consider how cosmic forces help shape our planet. When kilometer-scale hypervelocity comets and asteroids strike terrestrial planets, they shock the upper mantle and crust and impart plastic and brittle strain fields around the craters that can span hemispheres for the most energetic ones. Impact tectonic far field, or ITFF strains, are seen clearly on Mars, where there is no perpetual shifting of lithospheric plates like on Earth, where strain fields are also sometimes masked beneath sedimentary basins and deep oceans. Here we use Google Mars to map the Sirius, Sinai, and Salus Planum's Astrobleme, having volcanism uprange and mountain building downrange of a vast strewn field. Note the inclusion of Olympus Mons, Tharsis Montes, and Valley Marineris. Yellow lines marking interpreted bolide headings are extended downrange. The term Astrobleme was introduced by Robert Dietz, a plate-tectonic patriarch in the 1960s. He referred to these large structures on Earth as star wounds, from planetary impacts that leave eroded root structures including radial welting, folding, and faulting in expansive strain fields. He first used Astrobleme to describe the Vredefort structure, a 2.02 billion-year-old large Earth crater and radial strain field outcropping in South Africa, with ITFF strains still apparent in global magnetics. ITFF strain effects were first noticed in the North American plate from using current crustal movements derived from ground-fixed global positioning systems that measure horizontal drift and vertical crustal shifts across the globe. These data show that the American tectonic plates rotate in concert around the Chicxulub impact crater, about 150 kilometers diameter and 66 million years old, located off the tip of the Yucatan Peninsula in Mexico. This impact correlates with the mass extinction event on Earth occurring at the Mesozoic-Cenozoic era boundary, and it reset global tectonic movements. Pronounced strain signals are seen at 660, 1600, and 2900 kilometer radial distances in both GPS data and where earthquake seismic zones lie circumferential to the Chicxulub impact. The Chicxulub and Chesapeake impacts have helped shape the American tectonic plates. The Chicxulub impact staged a new geodynamic regime that continues operating today 66 million years later. Pronounced radial arching at 2,900 kilometer distance from both craters, and four-lane lithospheric wedges occurred downrange in both astroblemes. Interplate crustal seismogenic zones fall in a 1,600 kilometer ring around the Chicxulub crater. Chesapeake welting may account for episodic raising of the Colorado Plateau and the Central American Isthmus. North Atlantic Ocean transform faults change from concave to convex at the 66 million year isochron, indicating a reversal in the rotation direction of the North American plate after the Chicxulub event. Also note how the Atlantic Ocean floor physiography shows uniform growth from spreading along the mid-ocean ridge after the impact that continues today. The Chesapeake impact at 35.5 million years ago likely raised the Juniata culmination, where twinned calcite accounts for up to 8% bulk compaction downrange from the crater as measured in both Paleozoic and Mesozoic rocks from many studies. Ryan Mather and others in 2008 reported that rhenium-osmium radioisotopes measured in sulfide mineralized faults downrange in the Valley and Ridge province of Pennsylvania and New Jersey have ages clustering along a 32 plus or minus 3 million year old isochron. My MS thesis at the University of Connecticut 8 years before the discovery of the impact also showed how the Pennsylvania salient restores to the head of Chesapeake Bay. And so the hypotheses for a more inclusive plate tectonic theory are large hypervelocity bolide impacts on Earth and Mars have upper mantle ITFF strains reaching well beyond a crater that include structural compaction and wedging downrange of an oblique impact, and structural extension in large igneous provinces, or lifts, occurring uprange. Large hypervelocity bolide impacts on Earth and Mars produce brief, sudden, catastrophic tectonic episodes of basin and mountain formation that wane with time. And large hypervelocity bolide impacts on Earth can result in sudden geodynamic fluxes that persist for eons, even after subsequent events occur. I refer to the updated theory as punctuated tectonic equilibrium. That incorporates punctuated equilibria, the theory pertaining to biological evolution on Earth put forth by Gould and Eldridge in the 1970s, from observing isolated episodes of mass extinction followed by rapid speciation that occurred between longer periods of little or no change, called stasis. This graph shows how large bolide impacts coincide in time with episodic, large igneous provinces and large mass extinctions. Purple symbols are known impacts, blue are suspected ones, with large mass extinctions occurring in 30 to 50 million year cycles, and usually corresponding to the ends of either eras or periods. Punctuated equilibria differs from phyletic gradualism because the progression of life's complexity through time on Earth happened in a punctuated manner rather than with gradual randomness, and the same holds true for earthly tectonics. In characterizing the ITFF strain fields, I use seismic P-wave reflection and refraction paths through the upper mantle to constrain the structural geometry of the mantle wedging and welting. The largest astroblemes span 1/4 of the planet's surface, corresponding to seismic refraction paths bottoming out at mid-mantle depths of 1,300 kilometers. With respect to the anatomy of an astrobleme and Earth's layering, if we have an oblique bolide impact, we develop percussion shells and radial welting predicated on seismic wave refraction and reflection paths, and downrange mantle wedging and compaction occurs with uprange extension and magnetism. The Astrobleme anatomy incorporates the results of benchtop impact experiments using 60-millimeter diameter glass balls and a hardened steel projectile fired from a stabilized air pistol. Experimental incident angles are controlled by lifting the gun with respect to the target in 1/4 inch increments. At the maximum projectile velocity and a steep impact angle, a downward descending structural tongue, or foreland wedge, was formed that refracted back to the globe's surface as summarized to the right. This impact also produced antipodal cracks. With respect to the Astrobleme anatomy, downrange or foreland wedging occurring upon impact stems from refracted deep faults exceeding the Huguenot elastic limit, known as the HEL, the point in shock physics beyond which material behaves plastically in response to the application of intense pressures. Large hypervelocity impacts occur at speeds from 20 to 60 kilometers per second, but seismic waves transmit at speeds of only 4 to 9 kilometers per second. Consequently, pseudotachelite faults probably form the base of these foreland wedges that eventually become remote faulting and seismic disturbances occurring below the HEL. Large impacts produce low amplitude and long wavelength mantle ripples in fault wedging and bulk compaction downrange. Note in A above how lithosphere and crustal arching of 8 kilometers are only small deflections from a spherical surface. Now let's take a closer look at Mars. I used 5 global geophysical themes to define 13 large astroblemes, of which numbers 6 through 8 are shown to the right. The themes include colored surface imagery from the Viking missions in the 70s and 80s, and the digital geophysical themes from the Mars Global Survey in the late 90s, including global surface elevations and magnetic and gravity intensities. Here are 3 of the 13 Martian astroblemes illustrating the radial ITFF strain fields reaching 2,900 kilometer radius and beyond the craters. The first, Argyre Basin, heading of 357 degrees. Number 5, the Hellas Basin, heading 290 degrees. Number 12, the Syrian Sinai Planum, heading 130 degrees. A structural analysis of the interpreted fault traces was conducted on each. 7 out of 10 of the interpreted bolide headings indicate a southern source horizon and northern headings, which is consistent with the hemispheric physiographic dichotomy on Mars and other terrestrial planets and the Moon. The blue area is a 0-kilometer elevation ocean filling the northern hemisphere, as bombardment and accretion is more pronounced in the southern hemisphere. The Hellas Basin, the largest astrobleme, has a pronounced antipodal flare and large igneous province. This geographic map also helps place Olympus Mons and Valley Marineris into perspective. Here are hemisphere views of the Hellas Basin astrobleme and its antipodal lip. Note the interpreted headings with yellow lines extended downrange and the modeled poles, showing the Hellas antipodal lip on the opposite side of the Hellas Basin. The Viking imagery loaded into Google Mars together with the global magnetics by Connerty show hemisphere-spanning upper mantle faults offsetting planetary scale magnetic banding with associated lips likely caused by tectonic inheritance from the Utopia Planum astrobleme. Deep faults imparted by the Utopia event were later crosscut and reactivated by faulting from the younger Syria, Sinai, and Salus Planum's astrobleme, leading to plutonic and volcanic magmatism of Olympus Mons and Tharsis Montes at fault intersections. Now, returning to Earth, there is geophysical evidence that the Vredefort astrobleme has been an integral ongoing component of plate tectonics for over 2 billion years now. Whole Earth shear wave velocity models of the mantle shows that the largest, deepest magmatic plume rising off of Earth's molten outer core lies directly beneath the Vredefort astrobleme and continues to push magma upward beneath the East African Rift today, with flow directed parallel to current plate motions. 2 core pipes are the only 2 places on Earth where hot, molten material can follow straight conduits through the mantle from the core to the base of the lithosphere. The East African anchor structure is the largest by volume, with a pipe that is tilted in line with overlying lithospheric drift. The East African anchor structure straddles the Vredefort astrobleme, aligns with intensity anomalies in Earth's magnetic field, and shows congruency between magmatic flow and lithospheric drift. Now, with respect to the many suspected large bolide impacts on Earth, let's first look at the old Pacific realm, where there are at least 3 astroblemes interpreted based on geophysical coverage, with the oldest and most energetic having creased the seafloor and remagnetized vast regions of the Pacific Basin. Ocean floor isochrons by Moeller and others show how the seafloor has been folded with a central anticline plunging west and aligned with the heading of a strewn field comprising the mid-Pacific Mountains. Some of the oldest oceanic crust in the world lies downrange of the MPM-1 strewn field. Remagnetized ocean crust lies downrange of the strewn field that is flanked by well-delineated isochrons. And here's another view showing gray shade seafloor physiography of the remagnetized region relative to the strewn field. The southern hemisphere around South America has at least 3 more astroblemes, 2 by sea and 1 by land of Cretaceous and Younger ages, the Xingu Basin, Nazca, and South Georgia astroblemes. The suspected end Paleogene Nazca impact likely initiated the East Pacific rise, locally thickened and fractured oceanic crust, and has radial strains expressed in the curvature of South America. The suspected continental impact in the Xingu Basin, Brazil, has demonstrable ties to Cretaceous kimberlite intrusions, transcontinental fault systems, and a thickened wedge of crust lying downrange identified with seismic wave anomalies. Suspected South Georgia astrobleme, shown here using shaded gravitational intensity, may be a series of 3 impacts, with the central one defined with seismic reflection data. The seismic reflection profiles show central and radial uplifts like arc-type terrestrial impact structures. By far, though, the 2 most spectacular and expansive astroblemes include 2 suspected impacts correlating to major mass extinction events from the Kara Sea impact defining the Permian-Triassic era boundary and the Congo Basin impact defining the Triassic-Jurassic period boundary. 5,000-kilometer radial welts around these impacts now correspond to the location of transcontinental orogenic belts. The suspected Congo astrobleme at 201 million years helps spur the breakup of Pangaea. Global themes include E-topo-1 physiography, satellite-derived gravity and magnetic anomalies, and continental geology by era and ocean floor ages by Muller and others. Note how southern oceanic spreading ridges are circumferential at 5,000 kilometers distance. And here's a partial reconstruction of Pangaea using the Earth continental geology by era KMZ theme and map diamond occurrences shown as small red dots. And here's where the Congo Basin impact occurs relative to the Central Atlantic Magmatic Province, known as CAMP, which is a lip occurring between the 2,900 and 5,000 kilometer radius rings. The suspected Kara Sea astrobleme at 252 million years was also defined using E-topo-1 physiography, satellite-derived gravity and magnetic anomalies, and continental geology by era and seafloor age. And note how the ocean floor transform faults are circumferential to the impact crater. The Kara Sea astrobleme can be structurally reconstructed by removing subsequent ocean spreading having occurred in older and younger phases. The restored plates suggest that Greenland may have arisen from downrange impact wedging from this event. And now let's take a moment to see how much energy is needed to raise mountains in order for all of this to be plausible. Elliott, in 1976, estimated the gravitational energy expended to emplace the largest thrust sheet in the northern Rocky Mountains of Alberta, Canada, at about 10 to the 19th joules. Similarly, Sweden in 2013 estimated the annual energy needed to move tectonic plates on Earth to be on the order of 10 to the 19th joules, with 60% thought to be expended through earthquake seismicity. That's about 10 to the 12 joules per second that Earth expends moving its lithospheric plates around. In comparison, the instantaneous energy introduced into plate tectonics by 5 to 12 kilometer diameter asteroids impacting Earth at 30 kilometers per second is on the order of 10 to the 21 to 10 to the 23 joules as a fraction of the total energy of bolide flight before atmospheric entry that gets grounded upon impact. The fraction is calculated using a seismic efficiency factor, K, with cited ranges of values of 10 to the minus 1 or 10% to 10 to the minus 4. So grounded impact energy is equal to the seismic efficiency factor times the Newtonian formula for the kinetic energy of a moving body, taking into consideration its mass and its velocity. So at K equals 10%, Chicxulub grounded impact energy is estimated to be 10 to the 23 joules with a 150 kilometer crater and a 12 kilometer bolide. Chesapeake grounded impact energy is on the order of 10 to the 21 joules with a 40-kilometer crater and a 3-kilometer bolide. And so there's at least 1,000,000 times more energy than normal suddenly introduced into plate tectonic processes from a large impact than during stasis. The takeaways from all of this is that punctuated equilibrium is a more suitable guiding principle for terrestrial tectonics than uniformitarianism, the current guiding principle of geology. Very large hypervelocity comet and asteroid impacts on Earth and Mars impart ITFF strains and have geodynamic consequences that require accounting for in a more inclusive plate tectonic theory. Large bolide impacts likely help form mantle layering owing to repeated percussion and accretion. Earth's exterior layers may arise from bombardment and strain hardening in response to catastrophic cosmic impacts. And to conclude, mountain ranges and large basins can form suddenly in addition to slowly. Planets are occasionally subject to cosmic storms producing catastrophic geologic disruptions that are seen in both biological and tectonic records, and that may be the basis for ancient historical human accounts of seemingly improbable cataclysms like great floods, blood rain, and the prolonged severe climate changes. Dendrochronology and ice core chemical analysis show extreme atmospheric events have occurred 4 times over the past 5,000 years, with the volcanic winter of 536 BCE roughly correlating with the onset of the Dark Ages. I recommend the book, Comet Asteroid Impacts in Human Society. Thank you for your time, and keep watch on the southeast horizon. A special thanks to Ohio University Geological Sciences for jump-starting my career and hosting the 2023 OU Geology Alumni Symposium. My books are available on Amazon.com.